Hello. In this episode, I will show you how to find the xy intercepts, the equations of asymptotes, and using these to sketch the graph of rational functions. So we can start off by finding the intercepts by letting x and y go to 0. I like to set x equal to 0 because it seems to be easier to substitute this. Now notice that this goes through the origin, so I know that the y-intercept will also be 0, but let's take a look at what we will do instead. We'll set this equal to 0 on the left. So here, for this ratio to be 0, the top has to be 0. So it's the same as setting the numerator to 0, so you see that this leads to the same point. For the vertical asymptote, we set the denominator equal to 0. So therefore, x equals minus 4 will be the vertical asymptote. Now for the horizontal asymptote, we will take a look at the highest degree term. So in this case, they are both x's. So we can simply take either the coefficient of it, or we can just divide out those two terms and see what the ratio is. So this is 1. Therefore, the horizontal asymptote will be at y equals 1. Then we can put this onto the plot to the right. We have it passing the origin. We have a vertical asymptote, sorry, horizontal asymptote at x equals minus 4. And we have a horizontal asymptote at y equals 1. So do you see how the curve has to go through sort of like this bottom right hand quadrant? Because if I put it up here, it's not going to pass through the origin. So rational function has these sort of, I don't want to say inverse, but like opposite. So you know how they will go into opposite corners? So therefore, the other piece of curve will be up there. And we also know that it cannot be down there because otherwise there should be another x-intercepts. But we only have one. So that's the graph. So let's find out what the y-intercept is. This turns out to be 1 over negative 2. Basically, it's just negative 1/2. And we do the same by letting y go to 0. So notice that this is always going to be just setting the numerator to 0 for the case of rational function. I can move the minus x squared to the left and then square root both sides. And this time I end up with 2 x-intercepts. To find the vertical asymptote, we set the denominator equal to 0. Therefore, this is just x equals to 2. This is vertical. And for the horizontal asymptote, we take a look at the biggest degree term on the top and on the bottom. Now for this example, because the degree on the top is bigger than on the bottom, we have to use long division to find out what the oblique asymptote is. So I'm just going to rewrite this as negative x squared plus 1 over x minus 2. And I'm going to transfer it down here. I'm going to add a 0x just so that my terms line up when I divide. So the first partial quotient will be negative x followed by minus 2. So what you can say is y is basically the quotient on the top plus the remainder divided by the divisor. So you can actually rewrite it in this form, and you will see that this actually represents the oblique asymptote. And the remaining part, well, it doesn't really affect the way that we can sketch the graph. So just to be very specific, then you write down this to be the oblique asymptote. Now let's use all of this information to help us sketch the graph. So first of all, We have the y-intercept at -1/2. We have two x-intercepts at -1 and +1. We have a vertical asymptote at x equals 2. And then we have this oblique asymptote at y equals -x minus 2. So we can start at -2, and then we can go 45-degree slanted downwards, right? So if I connect this, let's try it again. So using these lines here, can you tell where I'm going to be drawing the curve through, the 3 points? Well, it has to be in this top part of the grid, right? Again, we have this sort of opposite effect, you know, like, I don't want to say vertical opposite angle, but it's like this V formation. So we should have, oh, let me zoom it in. So we should have this part of the curve here that kind of goes beyond that. So this tiny little thing over here. But literally, this should just keep on like this, you know. But because of the grid provided, I would just extend until there. So that's what this rational function look like. Okay, moving on. So let's find out what the y-intercept is when x equal to 0. This will be 0. So therefore, again, we have 0, 0. So we don't actually have to find this here. I know this will be 0. Okay, blah, blah, blah. I know that's going to be 0. You can actually test it out yourself. You will see that you will find x equal to 0. Now, for vertical asymptote, set the denominator equal to 0. So therefore, this will be the equation. For horizontal asymptote, because the degree on the top is bigger than the bottom, again, we've got to use long division. I can just add these terms to make sure that they are aligned. So here we have x. And then here, now, this is odd, right? Well, this is because we can actually use fraction here. So this will be like that. So the top will give you the equation of the oblique asymptote. And then let's put everything in on the grid. We have a vertical asymptote at 1/2. We have this oblique asymptote at x plus 1/2. So that means it starts from the origin, and then that means it's going to go up half and half. So for every 2 steps to the right, I'm going to go up once. So 2 right, 1 up. I can go the other way around. 2 left, 1 down. 2 left, 1 down. Okay, so you know that this is just 1, 2, 3, 4. So let's join these up. Oh, sorry, x plus 1/2, my bad. So this line needs to be shifted up by 1/2. So it starts at 1/2. And then that means at 1, it should be at 1. So now I can do 2 right, 1 up. 2 left, 1 down. Oh, what happened here? My line is not straight. Okay, this is the oblique asymptote. So I need to have the curve to pass through the origin. So the curve should go through this here. And then again, we have the sort of opposite pairing. So it might look something like this. Let's make this a bit nicer looking. Okay. So that's the sketch. D, you know the drill. Find the y-intercept. Now, problem is, this actually don't have a, there's no answer. This is undefined because we cannot divide by 0. So therefore, there is no y-intercept. And then you might be asking, why is that? Well, you'll find out soon. When I go to 0, we have 0 equals x squared plus 1. So that means the top equals to this here. And then if you try to do this part here, you will see that there's also no answer here. At least not in the real case. So no real solutions. So that means there are actually no xy intercepts. Okay? How odd. Now for vertical asymptote, it's easy because when you set the denominator to 0, it's already x equal to 0. And for horizontal asymptote, again, the power on the degree on the top is greater than the degree on the bottom, so we have to use polynomial division. This one is a simple case. Oh, I should add in a 0x. So this one is just 0, right? You could pull down the 0, but I'm just going to skip that term. And what do I put here? Okay, I can't actually put down anything here, can I? Because if I put any number here, it will become that many x's, but I actually have no x's here. So what I have to do is actually do 0. So if you want, you can write down this is just 0x, and then technically that's just a remainder. So that means the oblique asymptote is actually at y equals to x. So how do we sketch this graph? Okay, we have no intercepts. Well, so the vertical asymptote is actually right on this line. Okay, so we don't have to draw it. We already have the asymptote there. But if you want to be specific, then you can write down x equal to 0. And the oblique asymptote is y equals x. So we could just draw the 45-degree line across the corners. Okay. So how are we going to draw the graph? There's no xy intercepts, right? That's really odd. So what's going on? It's because, remember, there's actually an asymptote here. Maybe I will draw this over here. So now you can see that, oh, well, I can actually dissect the graph. Maybe either looking like this, right? Or like this. But actually, it cannot be these two parts because it will cross the x-intercepts. So we will choose this latter case. So go ahead and just draw the curves using these as guidelines. There you go. So it's possible to have a curve that doesn't go through the xy intercepts. All right. Now E is a challenging one. So we go through the same process to find the y-intercept. You let x equal to 0. So this would just be -1 on the top and 3 on the bottom. So we have this as our y-intercept. X-intercept. So you're just setting the denominator equals to 0. Now the problem is here. This has a cube here. So if you recall what we did before, this is actually factorizing a cubic. So some things that we can try is the factor theorem. So we can try 1 and -1, and then 1/3 and -1/3. But here it looks like -1 will work. So if you try, so if I just rewrite this as f of x, what I'm trying to do is replace this with f of -1. And this will give us, oh no, that's not what I want. I want 1 minus 2 minus 3. Actually, does it even work here? What, 3 plus 2 minus 1 doesn't work. Negative will also not work. So 1/3, would that work? No, it doesn't look like there will be rational roots. So let me just confirm that. Yeah, so actually for this here, the root is actually not that nice looking. It turns out that there's only one root, and this is the 3 sig fig answer. All right, so just move on to the vertical asymptote. We set the denominator equal to 0, and this time we end up with actually two of them. It's at plus or minus √3/2. For the horizontal asymptote, again, the degree on the top is bigger than the degree on the bottom. So we will use polynomial division to find out what it is. I'm just going to be rewriting this. Okay, so kind of want to do synthetic division this time. 3 to 0 minus 1. And then, no, but you see how this will be fraction now. So it's a bit annoying. Let me just switch it back to the long form. And we're going to have fractions too. So, well, it is a challenging question anyway. So 3 divided by -2 is, of course, this here. And there should be an x, so let me line this up. And then we will have this, because that's what we want. Times this by 3, it will be minus 9/2x. So again, we want a 2x squared, so it's going to be another -3/2. So we actually don't really care about the rest, but we can still finish it. And that is, if I add, it will be that here. So if you take a look at the quotient, that will be the oblique asymptote. So y equals -3/2x minus 3/2 is our oblique asymptote. So let's put all of these together. First we have 0 and -1/3 somewhere here. And for the x-intercept is around 0.5. Then we have two vertical asymptote, √3/2. Actually, square root, it's square root of 3/2, which gives us approximately 1.22. So roughly here, so let's say this is x equals √3/2. And then symmetrically, we have the negative here. the horizontal. No, we don't have horizontal. We have an oblique. So this is, maybe with decimal, it'd be easier to read. It's negative 1.5x minus 1.5. So that means we start off at 1.5. Sorry, negative 1.5. And then after one step, it should go down to negative 3, negative 4.5, so forth. And if I go back the other way, it will be a 0, 1.5, 3, 4.5. So notice that in order to pass through these intercepts, then this one down here has to be, this one here needs to be, can I do this a little bit better? Okay. And then it's gonna be this little piece over here, and where is the last piece? But there's only one x-intercept. Oh, I didn't realize if this is a double root or not. Okay. There's actually more to this question because I need to determine if there's any double roots. Because if there's a double root, then it actually doesn't go from negative to positive to back to negative. It will be maybe like positive to positive or negative to negative. And it turns out that I can't see what the graph looks like. Oh, interesting. Apparently, I have the graph all wrong. Okay, so the middle part, yeah, this part is actually more than what it meets the eye. So it turns out that it has this part here, so that doesn't intersect anything. And in the middle part, it's a little bit strange. Okay, so it's actually guided by these two asymptotes there. And in order to actually get this sort of curvature, to understand this, we will have to use calculus to help us see if whether it is decreasing or increasing or decreasing. Then we will actually get a more formal picture, like the one here. So notice that in the middle part, it actually does cross over the oblique asymptote. The oblique asymptote tells you about the behavior as it gets really, very small and when x gets very, very big. All right, so let's find the y-intercept. It's just -9. So I'm going to have to change this scale a little bit, otherwise it's not going to fit. And when y equals to 0, I'm just going to write down the numerator because the denominator always get multiplied out. So we have x equals to plus minus 3. Vertical asymptote, set the denominator to 0. So we have x equals 1. Vertical asymptote. Okay, the degree on the top is bigger than the degree on the bottom. So let's just divide. I'm going to rewrite it as minus x plus 1. So therefore, we have this as our oblique asymptote. So because of scale, it's a little bit different. Should I do 1, 2, 3, 4 here? Yeah. No, I'll keep it square. So we have our 0 and -9 down here, -3 and 0 there, 3, 0 here. Vertical asymptote at 1. Horizontal, vertical, oblique asymptote at -x minus 1. So we start at -x, and then it should go down 45-degree line. So I could do it, but I'm going to use some more points here. Okay, can you see how the curve is going to go? For this to intersect the x-intercept at -3, it needs to be something that looks like, I have to draw it from this way, I think. And then here, like that. Oh, I didn't pass the y-intercept, so that, let me draw it like this. Ooh, not good enough. It's definitely easier to start from the right hand side here. There. Kind of looks like a bridge. Okay. Y-intercept. Is 3. X-intercept is so we can factor this. So therefore x equals 0 or -6. 0. It shouldn't be 0. Otherwise, I should have captured that in the first case. Why is that? Oh yeah, of course. Because when x equals to what? That can't be right. Y-intercept is, oh, sorry, I did this wrong. This is 0. I was like, how come there's two y-intercepts? So therefore, I actually, in this case, be careful, I do have a second x-intercept, so I should still solve for it. So yeah, this right, so this one is redundant, and so this is redundant. And then we have -x, -6, and 0. Vertical asymptote, set the denominator equal to 0. That's that. Again, horizontal asymptote, we don't have one because the power on the top, the degree on the top is bigger than the bottom. So we do long division. It's technically 0, so we can just add +4. So this is the oblique asymptote. So we have the intercept at the origin, and then we have -6 and 0, so that means I have to use this as a possible scale. So this is the other x-intercepts. Then we have a vertical asymptote at x equals -2. And then x plus 4. So that means it starts at the origin and then it goes up to 4, 8, and 12. Whereas this way will be -4, -10, -8, and -10. So let's draw in this oblique asymptote. So can you see? This can't be right again. Sorry. This is wrong because I didn't shift it up 4. I looked at 4x instead of x plus 4. Okay, let's try this again. My apology. X plus 4 means it starts at 4, and then when it says 2, it will be add 2, add 2, add 2. So in the other direction, it goes this way here. So then in order to cross over the point here, this needs to be something like this. And then on the right hand side, I need to pass through 0. Can't see it because I deleted it. So it might look like that. Again, another bridge looking figure. And finally, sum that is not oblique. When x equal to 0, we find the y-intercept in SO. It's still 0 because it's on the top. Whatever is 0, well, I mean because the bottom is non-zero, we're okay. So 0 divided by 1 is still 0. But I'm going to set the denominator to, sorry, I'm going to set, I don't know why I'm doing it, but just do it anyway. So here you see that we have the same answer. Didn't have to because the top is linear, so of course I know there's only one solution. Vertical asymptote, we set the denominator to 0. In this case, you will see that this has no solutions. So therefore, no vertical asymptote. And for the horizontal asymptote, did I say horizontal asymptote just now? There are no vertical asymptote. For the horizontal asymptote, because the degree on the top is less than degree on the bottom, then it will just be y equals 0. So this time I could just do 1, 2, 3, 4 on my scale. Okay, I'm not gonna label everything. I'm just gonna label these ones here. So we have this intercept, and then we have no vertical asymptote. We have a horizontal asymptote at y equals 0, just to make it more obvious. So how in the world are we going to draw this graph here? It's kind of weird, right? And yeah, this one is special because if you use calculus, then we can actually further look at the behavior. But I believe it looks like this here. I'm not really sure because I will actually use calculus to confirm that as well. Yeah, I think it should look like this. I'm just going to graph it just in case. Good thing I checked. So, but there's no asymptote. It's because I plotted wrong. Yes, I'm correct, but it's not as drastic as my curve. It doesn't dip and doesn't go up as much, but it's that sort of structure of the curve. So maybe the dip is not as much. And the last one here. Now, this one looks a bit different, looks a bit odd. But for the intercepts, nothing changed. You substitute x equal to 0. It's 0 plus 3 over negative 2, so it's just negative 3 over 2. And likewise, you set y equal to 0. So there we have 0 equals 3x plus this. Now there's a couple ways of doing it. I'm going to move negative 3x to the left. And I'm going to multiply out the denominator. Expand. I'm going to divide everything by negative 3. And then factorize. So that means x equals 1 twice. This is a repeated root. So at 1 here, and we also have intercept at -3/2. Let me just label the x-intercept, the y-intercept. Oh, sorry, horizontal asymptote. Where is it? Still set the denominator to 0. So this will be a horizontal asymptote. Now, where is the vertical asymptote? Where is the horizontal asymptote? Well, we don't have a rational function just by itself, right? We have something plus something else. But did you recall that when we do polynomial division, this is what's on the top, this is the quotient, this was the remainder, and then the bottom is the divisor. Did you remember that when I showed you, I think, in part B or C? Okay. It's actually this form here. If it lets me scroll to that part. It's actually already in this form. So therefore, it already tells us what the oblique asymptote is. It's the first term. So this 3x is actually my oblique asymptote. So we have all the information that we need. I've already plotted the intercepts, and we have a vertical asymptote at x equals 2, followed by this oblique asymptote at 3x. So I can go up 3, go down 3. I think it's roughly here and roughly there. Oh no, look at the wrong point. Okay, so actually this should look like this. So that means I don't think my graph is going to be able to capture everything. So I'm just going to draw beyond that. I should choose a other scale. But here it would look like, it might look like this because I'm not sure how far this curve goes. And then there should be a part of the curve that is up there. Okay, and that's it, right? Yeah, that's it. Hope you learned something, and I'll catch you in my next video.